Indian Institute of Chennai chapter. I extend a warm welcome to each one of you to our today's webinar on the topic effect of trace elements in cast iron, Boon or Bane. We are truly delighted to have such an enthusiastic group of participants from various foundries. I would express my sincere thanks actually to our esteemed guest speaker, Mr. Balaguru Sendil, Deputy Manager R&D, Elkem, who has graciously agreed actually to share the valuable insights and expertise with us. Moving forward, actually, I'll request our chapter chairman, Mr. Vignesh Ramanan, to deliver the welcome address to the gathering.
Thank you, Raj. A very good afternoon, fellow Foundrymen. It gives me immense pleasure to welcome you all to today's online webinar organized by the Institute of Indian Foundrymen Chennai chapter. Today's topic, effects of trace elements in cast iron, Boon or Bane, is highly relevant to the industry as it addresses key factors impacting the production of quality castings. This discussion will undoubtedly empower foundries to elevate their standards and processes. We are privileged to have with us Mr. Balaguru Sendil, Deputy Manager R&D TCS Foundry from Elkem Innovation, a dynamic and spirited professional. Mr. Balaguru represents an organization renowned for its excellence in R&D and product quality. This webinar promises to be valuable learning, which will be an experience for all attendees. This marks our fifth webinar of the year out of 44 programs conducted by the chapter so far. We invite you all to actively engage, absorb the insights shared, and make the most of this opportunity. Once again, very warm welcome to everyone and look forward to an enriching session. Thank you.
Thank you, Chairman. Now I request actually Vice Chairman, Mr. P. Sendil Kumar, to introduce the speaker actually to the audience.
We see it's muted, sir. Muted.
Sendil, sir, you are muted.
Yeah. Good afternoon, fellow Foundrymen. It's immense pleasure to interact with you once again with you. Mr. Balaguru Sendil, we all know well-known personality in foundry industries. We may not require an introduction, but as a formality, we need to do that. He has done his master technology degree in specializing in foundry alloy production and specialized diploma in automation from Sweden. And he is a qualified research professional with more than 10 years of applied research experience in ferroalloy development and foundry metallurgy and cast iron metal treatment alloys. Presently working with Elkem as part of the global foundry innovation team and technical services deputy manager R&D and TCS. And his area of interest is thermal analysis of cast iron, metal treatment solutions for specialty HG and CGI and castings, process optimization using statistical tools, defect analysis of cast iron, foundry automation. He has conducted a lot of technical seminars for Elkem in collaboration with IIF for various chapters and various topics to optimization of metal treatment. He conducted a lot of customer training programs and wide variety of insightful topics related to metal treatment at some of Indian leading foundries like LMW, Synergy Green, HL Mando, CIE Automotive, Madras Engineering, SFL Auto, etc. Mr. Balaguru Sendil, the floor is yours.
Thank you. Hope I am audible.
Yes, sir.
Yes, sir, you're audible.
Yes. Thank you. Thank you, everyone, for taking the time to be here. Before I begin, I would like to thank the IIF Chennai chapter, its office bearers, and its dynamic president for giving me this opportunity to present on behalf of Elkem. We have selected the topic. I would share my screen now. I hope the screen is visible.
Yes.
Yes. Is it in presentation mode?
Yes, sir.
Yeah, thank you so much.
Yes, sir.
We have selected this topic, effect of trace elements in cast iron, because this is something that we see. There is a lot of need for this in the foundry industry at the moment. We are seeing a lot of challenges with respect to sourcing of quality raw materials, with respect to the demand by the developer or the customer for castings who have very stringent demands. So how do we meet these challenges? At Elkem, we are constantly trying to optimize our product portfolio to always be ahead of the trend. So my understanding and my target for today's session is to explain the fundamentals of what each element does, so that the foundry men, you are the expert who are doing the process in and out. You know your foundry much better than anybody else. Us coming from Elcom or any other company or any other consultant might come for a day or two, but I believe personally that if you have the sufficient knowledge transferred to you, you are the right person to take the right decision. So with this objective, I would like to begin the session. If you have any questions, please do note it down. We will definitely discuss it towards the end of the session. Thank you all for joining once again. I would like to begin now. Uh, so before I begin, as traditional and it is uh, right, we always acknowledge my colleagues as well as where I have taken the content for making this presentation. This is not only my work. A lot of people have contributed from Elkem, outside Elkem, globally to have made this content available for today's session. So with ado, I would like to start. So basically, I would like to first begin with elements in cast iron. So what do we mean by that? So if you look at the periodic table, I believe most of foundrymen might have this on top of your OES machine or in your chemical lab. There are different, it looks quite complex. Sometimes it can be a bit boring also, but us who are doing production regularly in and out, we no need to understand in depth the fundamental knowledge, but we need to have a basic understanding so that we are able to do a proper RCA to solve our issues. So if you look at it, there are more than 103 elements. People keep adding new elements to it, but cast iron typically deals about 30 elements. So if I categorize for cast iron, not on the element itself, for cast iron, based on cast iron, how do I group these elements? I can base it based on how much quantity or amount each element is present in our cast iron. I can also base it on what it is going to do the graphite shape and size. So this is very important. In case of gray iron, what it is going to affect the flake shape. It is going to make the flake bigger or smaller or fatter or thinner. So these are the impacts that each element can possess. And also on the matrix. What do I mean by matrix here? It is going to be about the ferrite and pearlite, which is going to get affected because of the element that are present in our metal. So based on this, we can classify the element that is associated to cast iron. So if I look at it, I will start with the basic primary elements. Everybody is aware of it. Carbon, silicon, manganese, sulfur, and phosphorus are the basic elements, irrespective of what grade, gray iron, ductile iron, CG iron, or ADI, SSF, whatever you make. These are the most primary elements involved. And then if we have an additional element called spheroidizing elements, which is nothing but an element which helps to form a nodule. So this is nothing but a nodularizing element. Magnesium, cerium, lanthanum, all this will help you to form a nodule. That is help to convert from a flake to a nodule. And then we have something called carbide promoting element. Chromium, vanadium, boron, all this such are carbide promoting. And then we have graphitizing elements, silicon, aluminum. This is on top of the primary elements. And then we have graphite shape deteriorating elements. The shape, as we discussed, the morphology, shape and size. Some elements can actually damage that shape and size. If I take, for example, chunky, cerium, all these elements, people are aware that these elements are actually can damage both the shape, size of my carbon as either in the shape of flake or in the nodule as in case of gray or ductile iron. So these are the various elements that are associated with our world of work, which is cast iron. So we can classify based it on how much amount of it is present, basically how much percentage it is present in our base metal, and also what it is going to do to my carbon shape and size, that is the graphite morphology, and also what it is going to do to the matrix. So based on this, we can broadly classify the elements what we deal in our day-to-day life into the following categories. I know it looks a bit complex. I would try to explain the terminologies, what is associated with each, what we are going to discuss further. So this is something that is associated to the basic world of element. We all know that we day in and day out work with this iron carbon alloy. So cast iron is not particularly one element, it is an alloy. Alloy meaning 2-3 elements are combined together. We all know that cast iron has the primary elements are carbon, and then we have silicon, and then we have certain other specialty elements to achieve certain mechanical properties, and then the rest is iron. So it is basically an alloy of multiple elements put together. And this diagram most of the time can look a bit intimidating, but I would try my best to explain what we are and what it is concerned to us. So I would take a pointer out. So this is the diagram that most of you might have studied in your academics, or you might have heard a lot about it during your career. So there is a lot of complex details here, but we will stick to the very basics of it. We are only worried about this portion of the curve. This portion of the diagram is where we are worried. In reality, we will be only worried about this. So I would like to give a definition of some of the key terminologies that are associated with this diagram, so that you will also be able to correlate to the element and what it is going to do. Because in the previous slide, we discussed there are some elements which can actually affect the graphite morphology, the graphite shape and size. To understand that, we need to understand this particular diagram, not to a very depth, to a surface level knowledge is more than enough to have a much better RCA done for defect analysis. So if I begin, there is this whole diagram actually helps me to see the solidification. Solidification meaning that when you are putting the liquid metal into a mold, you are basically allowing it to cool down to make it into a solid. So when it is cooling down, there are two aspects. It can be either stable or metastable. The one in the dotted line is metastable. The one with the black line is a stable solidification. We will come to the meaning of metastable later, but I would like everyone to understand here that this diagram basically helps me to understand the solidification behavior of my iron that I am going to melt and then cast. If I have a better understanding of this, I would be able to have a better control on my whole process down the line. Okay. So the next is graphite. We have been hearing this word graphite. What is it? Graphite is nothing but a carbon. The carbon is a very interesting element. Carbon, as we say, can exist in multiple forms, shapes in the universe. So you see your pencil lead is actually a carbon source. You have diamond, which is also a carbon. And we also are worried about graphite. With the graphite is most of the time it is associated to the world of cast iron. So how do we differentiate between a graphite, a lead, or a diamond? It is basically the structure in which it is present when it is solidified. In liquid state, all the atoms will be irregularly arranged, but when it is solidifying, it typically tends to form a very specific unique shape. And more the dense it is, better the hardness. So for example, this is graphite. If you take diamond, which will be much more complex. For the world of cast iron, we will stick only to graphite. So graphite is basically a hexagon structure. And when you have stable solidification, that is, when you are following the stable solidification behavior, you tend to have graphite. There is also something called as cementite. Cementite is nothing but it is a combination of iron plus carbon, which is a metastable. It is carbides. So if you look at it, the structure of this cementite is much more complex. It is much more dense. So this has a graphite has a much different mechanical properties, and carbide has a much different mechanical properties. If I say this would be much more softer, this would be much more harder. So the engineering application of these two are completely different. But in the world of cast iron, we have to ensure that we are having graphite. We also want some hardness, but we have to ensure how much we are getting and in what form and what shape. So we tend to target to achieve this particular graphite when we are allowing the carbon in our metal to come out. We are keeping about 3.5, 3.6 carbon in our base metal. 2% is completely 2% is completely dissolved into your liquid ion system. The rest is
IIF
going to
Chennai and
precipitate out.
90 ಜನ ಇದ್ದಾರೆ.
Shailesh, may I have to mute? Please go ahead, sir.
Yeah, please go ahead, sir. Sir, I think he's muted everybody. I'm sorry, Mr. Balaguru.
Shailesh,
You may have to
Shailesh is
unmute
setting
and start. Yeah.
Am I audible now?
Yeah, you're audible.
Yeah, sorry. about that.
Yeah.
So I was saying that we would like to get the carbon what we have in our liquid metal to come out as graphite and not as carbide. And at the moment, Indian foundries are more than capable to ensure that we have sufficient process control, sufficient methoding, sufficient competency in the shop floor to ensure that we don't have the fundamental problem of achieving high carbides. So this is what these two definition means. And then we get into a complex term that is called eutectic. It is nothing but when you are having one liquid, it simultaneously become two solid. So this is a very simplified definition of a eutectic meaning. So you basically have a liquid. When it is solidifying, it is not only becoming one solid, it can become two different solids. So in this case, I would say for us, when you have eutectic transformation, you have the liquid metal directly transforming to austenite plus graphite or cementite. So that is what it means. And then we have eutectoid transformation, that is nothing but where one solid can transforms into two different solid. So eutectic means liquid is transferring to two different solids. Eutectoid means where one solid itself is going to transform further into two different kinds of solids. So this is what the diagram mostly associates with. So eutectic, we all know it is operating in the range of 1153 in that degree Celsius, and eutectoid is about 740 degrees Celsius. So when this is what these terminologies means. And then we have another term called austenite. We discussed here, when you have eutectic transformation, the liquid directly transforms to austenite plus graphite. If you don't have eutectic, which have most of the time, we are either in hypo or hyper, the first thing that is supposed to form when the metal is cooling is austenite. It is nothing but it kind of a tree-like structure which grows. This is the first iron that is solidified. So you have predominantly what in our cast iron, we have iron. So when the iron solidifies first, the first thing that it forms is austenite. I don't know why we named it, but somebody decided to name it as such, which is okay. And what is the structure? Because when a metal is cooling down, everything is a crystal. So it'll have a definite structure as like graphite. See, it's a very defined structure when all the atoms. So you have austenite, which has this face-centered cubic. This terminology somebody might have studied or remembered in schools and colleges. This is what austenite is about. So when you are at this part of the curve, when you are operating in this range, that is less than 4.3 carbon equivalent, when your metal is beginning to solidify in your mold, the first thing that is going to form is this. And once it crosses this critical temperature, what it does, we are going to have the liquid, again the remaining liquid, transfer into two solids, either austenite plus graphite again. So the next thing is ferrite. Ferrite is an iron transformed at this region, eutectoid. So what happens is that the austenite, what you have here, that is going to further get transformed. So here one liquid is going to get transformed into two solids, eutectic. That is, one is austenite, this one and this one are going to come out. But what after sometimes this one, it is again going to get disintegrated into two parts. It can be a ferrite, which is nothing but the same thing as BCC. It is the transformation that happens typically at the eutectoid regions. And then we have pearlite. Pearlite, everybody is aware, it is a combination of ferrite plus carbides. So this is what it is going to be happening with the diagram. So we all know that austenite, ferrite, and graphite have a very specific structure. This pearlite, we know when a ferrite is going to form, it is going to be at eutectoid transformation. But this pearlite formation not only depends on the chemistry, as we are at chemistry here, means the elements, but also on the cooling parameters. So that is why when you try to knock out a bit early, you might end up with a different pearlite ratio. When you try to knock out a bit slow, you might tend to end up with a different pearlite. You are basically playing with the eutectoid temperatures. So these are the key terminologies that I would like to share here, because we are going to be more worried about graphite. We are going to worried about carbides. We are going to worried about pearlite, because all these three things, graphite, carbides, and pearlite, are highly depending on what element we are having in our cast iron. So this is something that we should try to understand. If you are not understanding it now, no problem. Elkem, we have a lot of videos, lot of animations which we are going to share very soon with the whole world. So we will be in a much better position to explain this. So this is with respect to the key terminologies that are associated with cast iron, which are relevant to the elements which is present in them. So if I take it, this diagram, I would like to modify a bit, because cast iron, as we told, is much more than just iron carbon or iron carbon silicon. So this diagram, it looks very nice here, but if I took it to a real world application, this is what it looks like. So this line here, what you see above between 1152 and 1154, this is a graphite line, and 1150 to 1148, it is a carbide cementite line. So if I look at the delta T, it is a 6-degree window in which we are operating. So this gap can either increase or narrow depending upon the elements that are associated in our world. I would like to first start with graphite promoters. So what do we mean by graphite promoters? These are elements which can ensure that the carbon what we are having in our metal, either 3.5, 3.6 or 3.2 in the case of gray iron, will come out as a graphite and not as a carbide. We can do that in one way by controlling the cooling mechanism. The other way, that cooling mechanism is mostly related to the methoding and gating, which we can do. That most of the time all foundries have fixed it, but sometimes because of the inconsistency in our charge mixes, we are able to have this element control also. So these are some of the elements which can actually be a graphitizing element. So the most common one I would like to address here is silicon. So what does silicon does? It promotes graphite, and silicon is some of the earliest form of inoculant. The plain ferrosilicon that still it is being used, still it is a very capable inoculant depending upon the foundry condition. If a foundry has a very nice or a very they have compromised on their methoding and gating and casting yield is not the area of concern for that foundry, then we can work with a very plain ferrosilicon based inoculant itself. So this is what I would like to say here is that silicon is one of the most strongest graphite promoting element, and it also stabilizes it. So these are three elements which actually enlarges the delta T. It not only all other elements will try to make this range close, which is very dangerous. We would like to have this range widened. So graphite promoter elements, this one are elements that we should try to have in our base metal. The next area of incidence, we have perlite promoters. So as we discussed in the matrix, when you are having eutectoid transformation, you have the chances of perlite to come. Perlites are nothing but which these are alternate layers of ferrite and cementite. Ferrite is soft, cementite is hard. In general, perlite will give you a mechanical properties of hardness. So there are some elements which can actually promote this irrespective of the cooling conditions. If you want to even knock out a bit slow, if you have certain elements, you can still achieve perlite. Or the other way around, if you want to knock out a bit early and then still you want to have ferrite, or then you can achieve this. So out of all these elements, what are the effect of each elements? So if I say manganese, titanium, copper, phosphorus, moly, tin, and lead, all this, and sorry, antimony, all this can actually help me to promote perlite. It is not that each element will have the same effect in promoting perlite. Manganese has the least effect in promoting perlite. Whereas if everybody in foundry knows that if you want to have perlite, you add copper. So this is the hierarchy in which it works. So if you have more of this particular element, you can actually further reduce your manganese. So let us come to a scenario where you have a charge mix or a scrap that you have procured, which has higher amount of this particular element. And you typically tend to keep a bath manganese of this much. And suddenly you see that you have a high amount of perlite. So the reason here is that even this can be 0.0005. The potency of this particular element is in promoting perlite is extremely high. So this is what I would like to show here. When you have this one, the window also kind of enlarges it. It pushes down the transition temperatures further down. So that is why it enables you to promote perlite. So this is also can be to some extent controlled with our process. The risk of having too much perlite or less perlite with respect to element control and with respect to cooling, at least we have two variables in which we can control it. So the foundrymen typically tend to take out the way which is suitable for them. If they are forced to use a certain type of scrap, then they can play out with a knockout time. So there are two variables at play here, which is in a way better. But unfortunately, the next one what we are picking is carbides. As I told, carbides are very hard and brittle, and we would like to have this completely under control. But in the area you can see here, chromium, titanium, vanadium, these are extremely carbide promoting element. This element will actually try to bring this delta T value further low, pushing all your graphite, all your carbon to come out not as graphite, but to have a metastable state, go into the metastable solidification and become carbides. So these elements are quite dangerous, and I would like to keep all this under control. So if I look at it, these two charts I have just put just to show that how much the temperature changes that can occur when you are actually going with an increase in chromium and increase in vanadium, and where it is going to intersect. So when you are having a challenge of increasing in chromium, you can expect how your eutectic temperatures are going to get affected. If it is going to get affected, the eutectic transformation will get affected. The further transformation of iron into either austenite, ferrite, graphite, everything will get further down the line affected. And how I can correct it post tapping with respect to magnesium in case of ductile iron, or with respect to inoculation in case of gray iron, or inoculation plus magnesium in case of ductile iron again. So this is something that we should try to keep in mind, that the carbide promoting elements reduces delta T, which is much dangerous. Now, I'm going to have a small slide on trace elements. So as of now, so far, we have discussed something interesting on the different elements associated with cast iron. We know the primary elements, and then we also talked about some carbide promoting elements. We also talked about graphite shape degenerating elements. And then we move to the iron carbon diagram to understand what is graphite, what is carbide. And then we also talked about eutectic transformation. We also talked about eutectile transformation, and then what is austenite, what is ferrite, and what is pearlite. The basic definitions we have understood, and how elements which can actually influence the iron carbon diagram we discussed, with respect to which elements which can actually push for more of graphite, that is graphitizing element. Silicon is a classical example for it. And then we also discussed about pearlite promoting elements. There are very strong pearlite promoters as well as mild pearlite promoters, and how we can work with that pearlite promoting elements. Either we control the elements or we change the cooling rate. That is with respect to the knocking parameters of the casting. There are two variables at play there. So the foundry has typically much better control or much better chances. And the third, we are talked about carbides. This carbide is very dangerous. Some elements actually make sure that your carbon is not coming out as graphite, in spite of you having correct methoding, correct gating, and correct process control. These elements will actually reduce the range, and then you have to have subsequent process changes, process control with respect to inoculation and magnesium corrections, so that you don't end up getting more carbides in your castings, which can actually affects the mechanical properties. So this is what we have discussed so far. Now I would like to define the term trace element. So what do I mean by trace elements? The minimum quantity or amount of a compound. In the first slide, we discussed how do I classify the elements in cast iron. Either first thing, how much they are present. And the second thing, what do they do to my morphology? And the third is, what do they do to my matrix? So trace elements are nothing but which is the minimum quantity present effectively at about less than 0.1%, which are present. So it is also known as subversive elements or deleterious elements, which is other terminologies used sometimes in Europe or American standards. So when you have inquiry for a casting, they might use this term. It is nothing but it is the same trace elements. It is the minimum quantity that is allowed, and anything above that can actually influence both the form. So element which affects what form carbon is precipitated. So the form here is that either it can come out as promote it as a graphite, or it can promote it as a carbide. Most of the time trace elements tend to promote it as a carbide, and even if it is promoted as a graphite, in during later cooling period, it can also influence the shape and size. So in spite of us having a graphite microstructure, when it is cooling down, it can actually make sure that the graphites have become too big, that is nodules have become extremely enlarged, more than 70 microns, or the flakes have become very thick. That is with respect to the size, and the element can also influence the shape of it. How round is the nodule? It could form a perfect nodule and then it could break it. It could form a perfect nodule and then have a spike on it, which is going to get dangerous. So this is what an element typically does. So a trace element is nothing but it is the minimum quantity present to cause damage to both my precipitation of carbon as well as the shape and size of my graphite. So this is what it is going to influence. Okay, I understand this is what trace elements, but how do I define it as a trace element? There has to be a logic in which this element is considered as a trace element. We know this element is a trace element because we have seen the element causing this problem. We have enough research work done in the past to correlate it. But there is one specific terminologies that is used in the research to understand which elements are trace elements. There could be many other trace elements with absolutely no impact on the said three aspects of the cast iron: the form, precipitation, form of carbon, the size and shape of graphite. There are many elements which will not even affect these three things. So those elements will also be present in less than 0.1%, but have no impact. So in spite of being trace, they are not causing me a problem. But there are some elements which causes a problem. So what is the differentiating factor between these two things which is causing a problem and the one thing that is not causing a problem? Is nothing but surface active elements. Again, another fancy terminology. It is nothing but element which reduces the surface tension of liquid iron will have a negative influence on graphite formation. Okay, what is surface tension? Before that, these are the elements, we'll come to that, which actually have a surface active elements which are kind of spoils the surface tension of a liquid iron. So what do I mean by surface tension? You can see here a water droplet. So the thing here is that, everybody is aware that water is a liquid. It doesn't have any shape or size. It takes the shape and size of the container in which it is stored. But when you are allowing the water to drizzle down in a form of droplet, it is always a perfect round, or it tries to be as round as possible. Why? It is because of surface tension. You might have also seen mosquitoes landing on water. Why? It is a liquid. How come the mosquito land on a water? Because the surface tension of the water is high. What do I mean here is that when it is a liquid, all the atoms are quite randomly orienting and then they are trying to just move around randomly. But the outer surface kind of bonds together and acts all inward. So this is what surface tension refers to. The same is applicable to cast iron. So when the metal is trying to cool down, we have all the atoms randomly moving around. So graphite will form a very specific hexagon structure. And then when this hexagon structure graphite is there, if you are having this sort of elements which will come and kill the surface tension, it will make sure that the gap is more here. So this thing will kind of go out and a round shape of a nodule can get affected. The same logic applies to a flake as well. So this is what a surface active element, which what it does is that it degenerates the shape and size of the carbon, which is a graphite. In case if the carbon, it can also do one thing more and ensure that we are not even having a graphite, we are having carbides. So that is also another feasibility with this elements, trace elements. So again, the term here is that the larger the atomic volume, the larger the impact. So what do I mean by here? I will explain in the upcoming slides. So as we discussed here, bismuth, lead, tin, antimony, arsenic, sulfur, selenium, beryllium, aluminum, all these are surface active elements. And we are aware that in Foundry, we are dealing with lead, we are dealing with tin, we are dealing with antimony, sulfur is a very important element we are dealing with. We are having tellurium. That is why when you are having quick cups to determine carbon equivalent, they don't advise you to put it back into your charge mix. So there is a reason to it. It is a surface active element. What it does is that it spoils the surface tension of liquid iron, meaning it kind of destroys the shape of a nodule, the nice round shape of a nodule, or a flake. It makes the flake kind of grow like a spike. It makes this, to be very clear, it makes the flake spiky, and that is the direct term in called as Winston graphite. We will discuss about that later. So this is what it does. One thing is that this is the hierarchy in which it does. So all these elements will not have the same impact. When we discussed about perlite promoting elements, we know for a fact copper is much more stronger in promoting perlite than manganese. And then we have antimony, we have arsenic, which are much more stronger than even copper. So this is the way in which it is promoting. Similarly, there is a way in which this element can actually kind of damage the surface tension. Bismuth is more in damaging the surface tension. This is not always a bad thing. This is also a good thing. That's why I had the topic. It is either Boon or Bane. In this case, it can be Boon. And then we also have sulfur. We have other elements in this order which can actually influence the surface tension of it. Antimony is a very classic example which can actually ensure that you don't you breaks up the surface tension and then you have good nodules. We will come to that in the later slides when we are discussing. The point here is that when you are having a large atomic number, large atomic weight, large atomic volume, the impact it can do to damage the surface tension is high, even when you have extremely low levels. So a bismuth at 0.0005 does much more either good or bad than aluminum at 0.1. So even at ppm level, this can be much more either useful or dangerous than this one. This is what the key takeaway here. And we know that cerium and magnesium also reduces the surface tension. This is the ability of magnesium and cerium to reduce the surface tension is called nothing but nodularization. But when you add too much, it reduces it too much and it causes a problem. It leads to metallurgical defects. So when it comes to ductile iron, it is always very advisable to keep the magnesium as low as possible, and also to use a very low magnesium grade. If you have anything above high, it kind of causes a lot of problem. So this is with respect to trace elements. The definition of a trace element, how much it should be present to damage both the precipitation of carbon as either graphite or carbide. In spite of it being precipitated as graphite, we are happy, but it can also influence the shape and size of that particular graphite. This is not called a trace element. All trace elements can be either good or bad. Most of the time, the bad trace elements typically tend to be a surface active elements. What do I mean by surface active elements? It kind of plays with the surface tension of the liquid iron. It kind of spoils the shape of it, which can be a benefit, which can also be a problem. 80% of the time, it is a problem. The benefit out of it is very less. We will discuss this in going ahead. So with this is with respect to the trace elements. I would like to now discuss a very not all the trace elements that are going, it's not possible to cover in 1 hour session, but the key ones which are causing a problem to us to run our foundry day by day, and what are the driving factors, because we should try to understand what it is causing this particular issue to rise up in our problem in our foundry metal. If you want to know more about this, please do reach out to us, any of us in Elkem. We will definitely be able to help you with that. I am not going to mention any solutions that can solve this, can solve that. I don't want to use this platform to promote any of our products, but you can always try to get to reach to us or anybody who's supplying materials to solve the problem. Okay. A major trend in automotive industry. If it would have been an online session, I would have taken feedback from the crowd. But here we are seeing a big trend in the Indian automotive industry. The Indian automotive industry is unique. Our conditions are unique. Our demands are unique. Our perceived value for a car is completely different. Our definitions are different. But we have a lot of changes happening. One is IoT. Everybody wants a smart connected car. So from your mobile phone itself, you can see what your car has done. This has been the trend since early 2020s or even late 2017s. So IoT is catching up. ADAS is a technology, adaptive cruise control is also being catching up. EV and hybridization is catching up. This can cause a lot of panic in foundries, but this is at a very I would say it's not going to push or propel forward in the acceleration rate what they deem. It's going to be a very slow adaptation. At least the EV hybridization is something that it will kind of propel fast. But these three things doesn't do anything for the foundry. Maybe for the foundrymen to be interested in procuring a car, this might be of interest. But the other thing that is going to kind of influence our world is safety. And this is something that we are very proud that our Indian manufacturers are able to deliver all these 5-star rated cars. So we want to have a car which is extremely safe, crash worthiness, which is also very the need for our road conditions. And then we also are quite worried about fuel efficiency. In fact, Marley had a very strong campaign on fuel efficiency is the major driving factor for a new car buyer. So this is also quite important. And to have this fuel efficiency, it is always better to have a lightweight car. But if you have a lightweight car, it is a compromise on safety. So there is always something that has to be mis and balanced. And the third thing is sustainability. We are talking, the automotive industry is talking a lot on sustainability. They want green casting, greener casting. So all these things, and they want more of recycled material to be used. So what is the impact of these three factors on our shop floor or on our process in foundries, especially in cast iron, gray or ductile? So if you look at it, you might have seen this picture, especially last month. You see in Tamil news channel, we had Mr. Velusamy from Mahindra presenting a lot on this. What is a high strength steel used in the latest Mahindra vehicles? What is mild steel, lightweight steel? So basically what they do is that when they are using this ultra high strength steel, which is actually very light in weight, but also very strong. So they achieve the target of being safe and fuel efficient. So this is what the automotive industry is going to go for. They are going to go for a very lightweight, high strength steel. So their major concerns of having a safer car at a much lower weight is achieved. So if you look at it, how are they achieving this high strength steel? They are actually microalloying, and one of the elements that they use for microalloying is chromium. It is good for the steel, but unfortunately, when we have that as a return scrap to us, it's a challenge. We go up one step ahead. Advanced high strength steel. What are they alloying it with? Additional on top of chromium, they are adding boron and titanium. So which is again good for the steel, but not so good for us. And then you have ultra high strength steel, which is going to be the future. It's going to be alloyed with much more amounts of titanium to achieve the strength of the steel per they have the term per tensile strength per, I forgot, per cubic weight or something. So they want to achieve this. So this is what the automotive industry is going to go ahead. They are going to go ahead with having ultra high strength steel. They are going to demand their steel suppliers to provide them with extremely thin but high strength steel. And their steel suppliers are other colleagues in the world of metallurgy. The steel industries are going to focus more on achieving this by microalloying with chromium, microalloying with boron, titanium, which is good for them, which is good for the automotive industry. But unfortunately, when it is going to come to us, there are some benefits, but we also must be aware of the drawbacks so that it doesn't kind of comes as a surprise to us. This we were expecting this transition to happen very slowly, but because of the third factor, sustainability, and our scrappage policy of car, this is actually driving these two factors to be adopted very fast. So the transition to a foundry, the impact on the foundry will be much faster. We are not so sure exactly when we are going to realize this impact, but some foundries have already started to impact, especially the bigger ones. They are more concerned about the trace elements like boron and titanium, which is actually causing a problem since they are using a lot of their own company scrap, and also a lot of scrap that they buy for sustainability purpose, recyclable scrap, off grade scraps. So how do we are going to counter it? So this is what I would like to start with. The first element here is lead. So the first thing, lead, is that if I take it, it is a quite heavy element. As I told, the more heavier, the more danger it can do. So I'm not going to say how much to be there, how much not to be there. That's a very typical, I think, a foundry. What I'm seeing is that people give thumb rules, maintain this much, maintain that much, your problem will be solved, which is correct. But I kind of feel that each foundry conditions are unique. I mean, the challenges are different. So it is better for them to understand what it can do so that they can take an informed decision. So here, if I take a lead, I take a base iron, I count how much eutectic cells are there, which is about 1600. I take the same base iron, I add about 0.1% of lead, I see a drastic drop in the number of cells that is counted. I take the base iron and then I inoculate it. Of course, I'm going to improve the cells, which is the case. But here, if I inoculate it, I am always not as good as the metal which doesn't have lead. So what it does, it kind of restricts the cell growth. It kind of makes my flake more spiky. So that is the danger when statin graphite. And Now I go to the world of ductile iron. This is a normal uh, ductile iron microstructure before inoculation, after nodularization, that is after magnesium treatment, before adding any inoculant. If I had 0.05% of lead, I would see this sort of a microstructure. You can see very thick flakes, a spiky kind of a flakes. So this is what typically it is there. And then I do an inoculation for it. I achieve a nodule count of 156. I'm not going to say which inoculant and which product. This is the condition that we are going to compare against. So the base is same, the rest is comparable. This is what happens when I keep on increasing the lead content. So if I normal inoculated, I am having 156 as my nodule count. If at 0.025 lead, I am having a drop in my nodule count. At 0.5, I am not seeing that much deterioration in my nodule count. So what it does is that it lowers my nodule count, but it does not actually affect the shape post inoculation. So if you are having high concentration of lead, the only thing you need to worry about is that the lead is not going to kind of destroy the roundness of a nodule. It is only going to reduce the number of nodules available. As you keep increasing the lead, the number of nodules available will decrease, and also it kind of promotes perlite. So this is what a lead does. In terms of gray iron, if your lead is high, what it is going to do, it is going to kill your number of eutectic cells, which again translates to not so very good uniform A microstructure. And in ductile iron, uninoculated condition, it is dangerous. When you are inoculating, up to some extent is manageable. More than that, it cannot be managed, and it only reduces your nodule count. It doesn't affect both the shape and it doesn't affect the shape of a nodule. So there are different inoculants that you can use to counter this problem of lead. You need to use a more capable inoculant which can overcome this to solve this problem of no nodule count. So this is with respect to lead. It's a very heavy element. It is very top up in the channel. And the tolerant level or the tolerance level can be different. How much of your liquid metal can tolerate lead? It can depend upon, as I told, your factor that you can measure is the nodule count drop. But if you are having inbuilt methoding kind of support, you are giving a larger feeder, or you are having a bigger riser, or the methoding has been done in such a way that this variations can be accommodated, then it cannot be as severe as where somebody who is operating at very thin margins. But moving ahead, looking at the competitive market, what we are having, I don't think so we can compromise on casting yield, because that's a huge cost. So we need to have all the casting yield as low as as high as possible. All our methoding highly optimized. The lead is going to increase in the future. If it is increasing, our conventional way of inoculations might not be very effective. We need to think about something different. This is where Elkem can come and help you, but we will not kind of say that as a thumb rule, use this or use that. It is case to case basis. So we will be much better, be able to much solve your problems at a very cheaper solutions. Please do approach us to know more. The next is tellurium. Again, tellurium is also not so bad when it comes to the impact of it. The base iron in this case at 800, base iron plus 0.01% of tellurium kind of completely killed it. Kind of made sure that there is no flicks. Everything was more into D&E type graphite, which is not required, which will have a different mechanical properties and not very useful for engineering applications. Okay, I take this condition and then I try to have my best inoculant. I use a strontium based, which is supposed to be the best inoculant in the market. I do that. I do end up solving the problem. I do get back a bit of type A, but it is not as good as the base iron. So this is as complete. This is not, though the cells have increased, the microstructure is not very favorable. So this, what it does, it again restricts the cell growth. It forms this spiky kind of a graphite when starting, which is going to kind of have a drastic problem with your mechanical properties, especially your tensile strengths. So if you are going to have samples drawn directly from your casting, then it's going to have a problem. Then you are going to have for ductile iron. Again, it causes the same thing. The conditions are the same. If I add this much, it is going to kill my nodule shapes. Okay. Then I am going to inoculate it. At 0.003 let, my nodule count is 90. At 0.01, my nodule count has dropped to 68. What it does, again, it is very similar to the previous element, lowest nodule count. It doesn't have any shape or impact on the, it doesn't have any impact on the size and shape of a nodule. It only kind of lowers the number of nodules available to be calibrated as a nodule, good nodule. It not only increases perlite, it also increases the potential of carbides. So this is again a dangerous element, tellurium. That is why it is very, when we say it is deep, most of the time you can see carbides. The same can be applicable here. If you etch this much properly, you will be able to see a much lower nodule count. When you have a lower nodule count, the tendency for carbides are quite high. So this is what it is going to do to your base metal. Tellurium is much more dangerous than the previous element we discussed. The same condition in there, the nodule count was 156. We were seeing about 150 plus nodule count. Here you can see how even in spite of it being so low, it is having a drastic impact on the microstructure. So tellurium is not at all advisable to be added. And the primary source for this is not going to come from any scrap. It is going to come from only the cups, what we have, the thermal cups, the quick cups, what we have in our shop floor. We try to segregate it out and throw it. We don't want to add 1 cup per tapping to increase the charge. That is also not required, because this will slowly keep building up in your charge mix. It will go to your returns and then kind of spoil the further treatments down the line. So this is tellurium. The next one is bismuth. Bismuth, as I told, it can do good things, it can do bad things. It is also quite heavy, atomic weight is high. And then if I do base iron for gray iron, this is what it does at 0.05 bismuth. And I inoculate it, it is about not very great. It restricts, it causes a lot of uncooled structures. But when it comes to ductile iron, this is what the bismuth microstructure looks like. After having 0.05 bismuth, it is not a very great microstructure. But when I inoculate it, I achieve this. But the advantage of bismuth is that, if you can see here, is that the nodule count has improved from 156 to 178 with inclusion of 0.025 bismuth. When I double the bismuth to about 0.05, I see almost a strategic jump in the nodule count. What it does is that it needs definitely rare earth to be very effective. Bismuth alone doesn't do anything. So when you are having bismuth coming from your charge mix, this alone cannot do anything. But bismuth combined with rare earth, which is going to be for either from your magnesium or your inoculant, or the bismuth based inoculant itself will have rare earth in it. This combination can actually increase your nodule count, can give smaller and better rounded nodules. So it kinda breaks up the big nodules into smaller ones, and then you have more nodule count, and all the nodules, the average size of the nodule come down by about 10 to 15 microns. So this is the advantages of having bismuth, but the drawback here is that bismuth alone cannot do this. It definitely needs rare earth to be effective. The mechanism in which it works is quite complex. We have much better understanding of that in Elkem. That's another separate topic we can discuss forward. The risk of what it does is that when you do not have rare earth to counter this bismuth or take advantages of the bismuth that is present, you are significantly increasing the risk of being spiky. So this is more visible in the case of gray iron. In gray iron, bismuth causes real problems because you do not have that much amount of rare earth to counter it. Whereas in ductile iron, you can escape with it. That is why we still have bismuth-based inoculant in the market, which kinds of ensure that it breaks a big nodule into small ones and then improves the nodule count. So this is the logic in which the bismuth can be taken a benefit for ductile iron when it is combined with gray iron, with the rare earth, and in gray iron, it is quite challenging. So this is with respect to the bismuth. The source of bismuth is again, can come from scrap as well. The next is antimony. So antimony is SP. Antimony, I can say that it does only one thing very good. You can see here the base metal with no antimony, and then you have base metal with 0.05 antimony. In case of gray iron, it doesn't spoil the shape and size of the flake. It doesn't cause carbides. Only thing it does is that it is not, this effect is not like bismuth, tellurium or lead. This effect is very clear. It promotes and stabilizes perlite. So if you want to achieve a perlitic material, just add antimony for gray iron. Perlite, as I told, it is the strongest promoter of perlite. Even at extremely low addition percentage, you will end up with getting perlite. So this is the advantage of it. The disadvantages of it is that if you are not able to control, where you are not being able to control how much it is coming, where it is coming from, then you might end up getting higher amounts of perlite, which can cause problem. So when you are seeing a rise in antimony from your liquid metal, it is advisable to keep lowering the manganese or copper to make sure that you don't overdo it. So this there is no negative effect of antimony on the microstructure for gray iron with respect to the shape and size, as well as on the chilling tendency. So it just does promotes perlite. The only thing it does is that, and which is manageable. But when it comes to again ductile iron, we all know that when you are having antimony, you can actually break up chunky. When you are having heavy section casting, people try to advise to add antimony so that you don't have all the nodules which are kind of joining together. When you have sufficient cooling time, that is in the thick section, all the nodules will join together, form a big nodule, and then still it has sufficient time to cool, it can kind of form a chunky. So to solve this problem, there is a typical suggestion to add antimony, but what it does is that it kind of promotes perlites along with it. So if you're trying to achieve a ferritic grade for your application, and then you are seeing a problem of chunky and you want to solve it with antimony, which can get solved, but again it can also promote perlite. It will definitely promote perlite, and then you need to play with your knockout to do correction for this, which I don't know. It causes more damages than it requires more process control to have good ferritic grade castings made with antimony. It is better to have control this with inoculation. So that is what I would like to say with respect to antimony. When it comes to gray iron, very strong perlite promoter, no influence on the shape and size. In case of ductile iron, of course, it can boost the nodule count. If you keep increasing it, it can increase the nodule count even at very thick regions, thick section castings, windmill, ductile iron, pipe fittings, all these areas, it can help to increase. But the drawback is that it's a very strong perlite promoter. So if you're trying to take casting samples from there and then do tensile strength, you might end up with challenges. So this is antimony. Then the next one is arsenic. So arsenic, it has no significant impact as such in gray iron. This is not a concern for gray iron foundries. Inoculate, this is my nodule count for this condition. The base is such. When I'm adding arsenic, I don't see that much. It actually kind of at 0.1% does a bit of refinement. But if I keep increasing it further, I see a drop. It has a very similar effect as antimony, kind of very strong perlitic promoter. It promotes perlite, but it is not as good as antimony. It is much weaker, and it kind of very section sensitivity. If you have thick sections, it will not do the work, whereas antimony will do the work, arsenic will not do the work. So that is where this kind of comes here. It is not in the top of the matrix. It's not even considered here. It promotes perlite, but it is also very strong chill promoter in thin sections. So this, how do I select arsenic if it is coming high from my trace elements, from my liquid metal, for whatever reason? Then for gray iron, I would not be that much worried about it, because it's not even a very strong perlite promoter, and it can be highly sensitive to section thickness. So the definition of thin here is quite narrow. So that is not even considered for typical operational range in gray iron. So you can run with arsenic. It's not a problem. The effect of arsenic is also connected to manganese. So this chart I have put here. So you can see that it kind of promotes carbide in this particular range when you are operating from 0 to 0.15%. And then you are having a round bar diameter of about 1 inches, 25 mm. So once you go down, once you have much thinner particles, less than 25 mm, about 12.5 mm, then the percentage of perlite will be high. At the same time, you also get into a region of this one, carbides. So you have to kind of correlate this to the amount of manganese that is going to be present to have neutralized this. So you cannot have high manganese and then arsenic high. Or you can think that my manganese is under control, but still I'm getting a issue of perlite, I'm getting a issue of chill. Then we try to see that whether the arsenic content has increased or not. So this is arsenic. The next one is the titanium. This is very, very important. Titanium is much more dangerous. It is more dangerous in the way it is affecting us because this is one of the most strongest element the steel industry is adopting to achieve their strength, uh, achieve their target of having lightweight, high strength steel. So titanium, we have to always keep a lookout for it, and this is going to come. It has already come, and what we are going to do to solve it. So titanium, if I look at it, base iron at about 0.1% of titanium, which is not bad actually. It does a bit of refinement for gray iron microstructure. So I can say that it kind of graphitizes the matrix maximum effort at 0.1%. But if I keep increasing it, 0.2, 0.3, because in the past, people have used titanium when they see that the casting surface finish, especially in gray iron, is not very great. After machining, they want to do a bit of refinement. It is still advisable to add some amount of titanium or chromium to achieve the matrix refinement, microstructure refinement, and everything, graphite refinement as well. But that is about 0.1%. When you are using high scrap with higher rate of scraps in your charge, and then that particular scrap has high titanium, that you are getting it automatically. Then you should control the titanium from all other raw materials that you are having. The titanium can come from your recarburizers, from your pig iron, from your returns buildup, from your inoculant, from your poorly made magnesium. All these things are going to give you titanium in it. So how are you going to control it? That is very important, because so far we have been happy to use the whatever material we have. We are getting titanium from there. Our base titanium was low, but now the base titanium is going to keep increasing. Then we need to have much better focus and control on all that other variables to control titanium. So as I told, 0.2, 0.3, it makes it further worse. You can see for yourself how the microstructure goes bad. It reduces the cell size, promote degraphite, increases chill. So for gray iron, titanium is going to be a very big problem unless you are able to control it, or unless you are able to neutralize the effect of titanium with proper preconditioning. When you are going to go for ductile iron, what it does, I'm sorry, in gray iron itself, this is the base conditions. When I add inoculant to it, this is the base and this is directly post inoculant. This is 0.1 and this is what I'm going to do with inoculant. Of course, I can kind of improve it with good inoculant, but the percentage, if it's going to keep increasing, my inoculant is also going to struggle. At 0.3 titanium, I'm going to see a bit of struggle. So it does refinement. It does a bit of refinement to your matrix. Higher levels can be tolerant in gray iron as compared to ductile iron. It's more dangerous there. In gray iron, the amount of danger can be tolerated. You can see the microstructure even at 0.3 titanium. I am able to kind of tolerate it, but be aware that I used a very powerful inoculant, or we used a very powerful inoculant to get this microstructure. A simple silicon calcium barium will not be able to get this microstructure. How do I neutralize titanium with respect to gray iron is that I can also kind of increase the sulfur in my charge mix in my base metal to neutralize the negative impact of titanium. That is, the degraphite formation can be nullified with good inoculant, as well as kind of having a bit of more sulfur in your base metal. So this is again subjective to the foundry conditions, to the grade that they are making, to the type of casting, to the type of layout of molds that they are having, their pattern methoding and everything. So that's what, if we can solve this problem, when you are saying that you are having issues of titanium, we have to be very clear. It is not always a bad thing. It does refinement to your matrix. Higher levels of titaniums can be tolerated in gray iron as compared to ductile iron. It is possible, and the inoculation and sulfur can actually kind of reduce the impact of it. In ductile iron though, titanium will definitely kind of reduce your nodule count. It gives the reversal, it promotes or it facilitates the reversal of a flake to a nodule. It reduces nodule count, nodularity, promotes not only reduces it, it promotes degenerated graphite, it promotes CGI, and the most major problem is that when you are having titanium, it lowers the tolerances of other trace elements. So the liquid metal basically can tolerate certain amount of lead, arsenic, antimony, bismuth, all these things. But once your titanium has that, the amount of tolerance your liquid metal inherently has will come down. So that is why it is more dangerous in ductile iron to control this titanium to as much as low as possible. So this condition of 0.003 titanium, which gives me 95 nodal count, this same condition can brought down to 85, because my other trace elements are present in normal conditions. that can be tolerated, but with titanium additions that cannot be tolerated, or the tolerance level drops. So this is the problem of titanium in ductile iron. Quickly on chromium and zinc. Chromium, we are all aware, it's a very strong carbide promoter, which is going to play with the delta T. You have high chromium, especially in ductile iron, you are going to run into the problem of having high carbides. It also increases the chilling. It segregates to the grain boundaries very heavily, and this effect can be highly correlated to manganese. So the effect of this can be very similar. So chromium, typically we tend to keep it less than 0.1. We don't want to have more of that. It can kind of combine with manganese and then segregate to the grain boundaries, doesn't allow the metal to solidify. Your solidification temperature will come down. Because of that, you might end up with getting some sort of micro shrinkages and micro porosities. So that is a real world problem of having high chromium. But a bit of chromium can 0.1 0.15% of chromium in gray iron can cause a bit of matrix refinement, which is good if you're trying to have good surface finish post machining. So that is the advantages, and mostly in ductile iron it has a very strong disadvantage. Zinc, we know it is coming because of coated scrap. It is an environmental health problem. When you're trying to melt it, it is going to give a lot of fumes. It can condense, and it can actually make sure people with refractory lining background know that when they have a bit of zinc coming, it can spoil your furnace lining and it can lead to furnace breakdown. When you have zinc, it kind of spoils the magnesium recovery as well. So these two things are going to be associated with steel, and this can actually cause real damage to your foundry. The last one is that manganese. So manganese, I would not call it a trace element at this point. It is actually a part of the ductile iron system, but I have mentioned it here because we are seeing a lot of steel scrap with manganese, which is the most primary element. Then only they try to add titanium, boron. So manganese is the first thing that they add. So it kind of promotes intercellular carbides in thick section, segregates to the grain boundaries, especially in ductile iron, leading to a lot of porosities, inclusions, which will actually affect your mechanical properties, especially the elongation. So it increases the hardness variation within a casting. And for ferritic grades, it is very advisable to keep it as low as possible. Manganese also must be adjusted with respect to the silicon content. So if you look at it, the maximum wall thickness here, if I want to have a 10 mm casting and my silicon is 2.5, then I should have a manganese in this range. But for the same thing, if I increase the silicon percentage, I can tolerate more amount of manganese. So this tolerance has to be achieved of how much manganese can be tolerated with respect to the silicon content. Okay, this is quite important and a significant element, boron. So if you look at it, boron is also steel people are allowing with it. So for base iron in gray iron microstructure, boron is there, not very significant impact. But in ductile iron, we have different conditions of 7 mm, 15 mm, 30 mm, 50 and 75, and boron of 0.001, 0.005, and 0.1. So what it does is here is that if I compare the 7 mm from the first and the last one, it makes this looks more pearlitic, this look more ferritic. That's what it does. Boron promotes ferrite in pearlitic irons and pearlite in ferrite irons. It does that. It kinda, as the section sensitive, as you keep increasing the boron, it kinda makes sure that your ferrite becomes pearlite and pearlite becomes ferrite. What it does, the understanding of that is still under research. We are still trying to understand the mechanism in which it is doing so, and it is a very, very strong carbide promoter. So you have to ensure all other carbide promoting elements are kept under control. You operate with a very thin margin of eutectic temperatures, and you have to ensure you are casting it within that particular range. If you are having high boron, and then it kind of spoils the shape of the graphite, and that is more visible when you are having thick sections. So here that is not that much problem of graphite degeneration, but here I am having a graphite degenerated. You can see here degenerated graphite, you can see here degenerated graphite. These two regions, I am seeing that even a 0.01 boron and almost 0.1 boron starts to dangerous. It can kind of spoil the shape of my graphite, and which is going to adversely affect the mechanical properties. When I have different mechanical properties, my machinability will come down. Machinability comes down, then the casting service life also will come down. So this is the impact of boron. We have still having a lot of details on it. If you are interested, please do reach out to us on all the trace elements that we have discussed. We will be able to we are more than happy to help you with that. it does not give a higher nodal count. There are some literature which says that if I have boron, it increases my nodal count. We have not seen that so far in Elkem, but we are still open and we are still working, and we can say quite confidently we do not see any evidence to suggest the fact that it gives high nodal count. Not so. It kind of has the drawbacks outweigh the benefits here. So this is our technical information sheet. People have seen this. We have updated this. This is the old one. I have not put the new one in. We have a lot of details. We have a lot of technical information sheets which we can share with customers, which has summarized of whatever we have discussed, very crisp and neatly written, so that you can kind of use it as your cheat sheet in your day-to-day Foundry operations. And to summarize, finally, a trace element is something that is less than 0.1. A trace element influences the carbon precipitation and the graphite size and shape. Carbon precipitation is that either carbon as graphite or carbide. Even if it is graphite, what size and shape can be influenced by trace element. One trace element can have several effects. Interaction often occurs between trace elements. They do not act alone. They synergize manganese with arsenic. There is a very nice equation, Tillman's equation, which you can use to keep a track of how these trace elements interact. And then we have surface active elements, which are going to affect the graphite shape. Surface active elements we discussed, it plays with the surface tension. And the tolerance level of all these elements keep changing from foundry to foundry, depending upon the melting condition and charging practice. So one foundry will operate at even higher level of trace elements much better than the other foundry because of their charging and melting conditions, because of their holding pattern, because of the size of the furnace. So these are the impact, and the tolerance can level decreased with increasing section size. So again, the same is applicable. When you're having thin casting, you might get away with it. When you're having thick casting, you might see a problem. So titanium is the most dangerous. It reduces the tolerance for all elements. So this is the most dangerous aspect of titanium. As of now, we should try to focus to control, or how do I optimize titanium in my process. So this is the final slide. And we have this is just to give details to people who are interested how to contact us. We are present all over the country. This is the put the number and mail ID of the person, our team who's present all over the India. We have in South of India and Middle East. We have in Pune, North India. We have Chandan who's handling East and Central. We have dedicated person in Kolhapur. We have Gujarat, Ahmedabad, Rajkot, and then North India is fully covered. And if you have any doubts, you can also reach out to me. I'm the technical customer service manager for Elkem. And we have also another team of technical customer service people, so who can also reach out and help. So once again, I would like to thank the IIF Chennai chapter for giving me this opportunity. I tried to deliver. I hope I tried to achieve what I intend to achieve. I wanted to transfer the basic knowledge so that people in Foundry can utilize this and then decide their right course of action on how to control. If they want any guidance, we are available 24/7 to help and assist. So thank you. I do take questions. I'm open now. If you have any questions, please feel free to ask.
Sir, Balaguru sir, thanks for the presentation, but there were a few questions in the chat box, sir.
Yes, sir. I had one screen, so I was not able to see those.
Can I ask a question, Mr. Balaguru? This is Shivgopal.
Sure, go ahead.
Yeah, see, in your, thank you. That's a wonderful narration of wonderful talk on both irons and the influence of all the elements. See, during the course of the talk, you said that why the phase austenate is named, you do not know it. I think you can make a note of it. As a metallurgist only, I'm telling. It is after one British metallurgist, Sir William Chandler Roberts Austin. Roberts Austin, he is known as, and he is the first person who have developed the iron carbon diagram in somewhere in 1840s. And after him only the austenite is named. Kindly make a note of it. Maybe this will be helping you in your same slide presentations in future. Roberts Austin.
Sir, I'm aware of that name, but that is condensed. The claim is still.
You said, No.
Okay,
You
thank
said
you.
that.
I'll make a note of it. Thank you. Any other?
Sir, let's not make it
That is-
too much this thing. It's the information is noted, sir. We can please move on. Thanks.
That is one thing. Second point is more emphasis was given on the titanium. My question is most of this Bhutanese and most of the Meghalaya-based iron, ferroalloys which are made more rich in titanium. For the benefit of all the foundrymen who are participants in this forum, I wish to highlight this, that the titanium is coming from the ferrosilicon and most of the ferroalloys which are produced in this part of the region, because they are employing titaniferous iron ores as the raw material for their manufacture of ferroalloys. So how do we control it? Well said. You have wonderfully clarified it by increasing the sulfur, which is accommodatable in the case of gray iron only, if not the case with ductile iron. Only these are the two observations which I wanted to highlight to you, sir. And third is this one. Boron, bismuth. Bismuth, Elkem has a product for improving. I mean, not only Elkem, most of the suppliers do have it these days.
Sir, Mr. Sivagopal, sir, excuse
Yeah.
me. Sir, I would request you to restrict it to
Yeah,
questions
tell me,
only.
sir.
Otherwise, the questions or other things can be delivered by Mr. Balaguru. Thank you. Any questions alone you may ask.
Yeah, the
Please,
question
sir.
is, bismuth can be taken as a trace element or a alloying element? That is the question.
Thank you, sir. Mr. Balaguru, you may please answer that.
I would take it as an alloying element and not as a trace element. I would introduce it as an alloying element and not it as a trace element. Trace element is something that I cannot introduce. Alloying is something I can introduce. That is the difference. But if it is coming as an alloying element, as a trace element, then I need to counter it.
Yeah, then that is okay. That is okay. That is what I was expecting. Actually, it cannot be counted as a trace element. It is only a alloying element. You're right. And one more question I have. I will put only question as the forum coordinator says. There will be in larger thickness gray iron castings like this one piston blocks, engine blocks. There is a carbon pullout problem. How do we counter that with these? Adjustment of alloying elements or trace elements.
Sir, again, I'm not going to answer that question because I don't have enough data to answer that question. When you have a problem, that's why I put the entire team's contact, or you can approach Elkem. We'll come make a visit and solve. As such, I don't give any thumb rules.
We're already attending that engine blocks manufacturers. There are 5-6 people only are there in India. So they do have this during the machining. There will be lots and lots of carbon pullout problem. So that is the typical of Indian engine blocks which are manufactured. Whereas the Belgium made ones meant for the Maruti are not having that. So do you have any this one answer for that? You can always give me.
Sir, like
Sir,
he
I'm
said, I
advised
think
by my
people
team
can
not to
get in
answer
touch with
that
him.
question.
Mr.
Yes, sir.
Balaguru, the people who are wanting the answer can get in touch with you and you can answer that.
Yes.
It's all right. You've already told that. Sir,
Hello.
you can move on. Anybody else has any questions?
Hello.
Yes, sir.
Yes, Mrs. Subrata. Yes.
Yeah. Sir, there is any effect in the trace element in molten iron?
Sir, as such, molten iron will not have any effect, but we are going to cool the molten iron, solidify it, so it is going to have an impact. The only element which is going to cause in molten state is the zinc that is going to affect the lining.
Sir, I am not asking the molten. I am asking for mottled iron, mottled.
I am not sure about that, sir, but you can get in touch with us later. We'll be able to help you.
Okay, sir. Sure.
I will make a note of your request, sir, and I will ensure my Eastern team gets in contact with you.
Sure. Thank you, sir. Thank you.
Any further questions, sir?
Hello, sir. Hello. Sir,
Yes, Mr.
my
Ravi Shankar.
Chaitanya.
Sir, I have one question, sir.
Sir, in gray, more than 20% borings using effect, sir.
Sir, I didn't get your question, sir. Please, can you repeat?
Sir, in gray,
Ah,
more than 20% borings remelted.
okay.
Sir, different for like
You're asking if it is okay?
like porosity, linkage.
Mr. Chetan, it is not very audible. Can you please repeat it, please? Sorry.
Mute பண்ணிடுறேன்.
Sir, in gray. Hello. Hello.
Sir, might be you
Hello.
can send your message in the WhatsApp, sorry, in the chat box, sir, actually, because your network has some issues. I
Hello,
think
hello.
your
Sorry.
voice is not
Sir.
clear.
Hello.
Hello.
Sir, in gray,
Boring you can use. There is no restriction unless the boring is very clean, free from oil contamination or any
Yes, sir.
painting or any coolant mixed with that one. There are foundries with the induction furnace who are using totally boring only. They can recover about to 80 to 90%. And the slag formation is slightly higher because the very thin section getting oxidized. So unless you clean the boring, you cannot use it.
Okay. Okay, sir.
Yes,
Thank
sir. Thank you, sir, for that answer. You can use borings. Borings is not the problem. It is the coolant that is the problem. It is the acids in
Yes.
the coolant that is the problem. Those are
Yes.
sulfur and other harmful
Right.
element based. So if you are
Right.
able to negotiate that, it's a good thing. There's another problems
Yes.
with boring is purely the melting aspect. Whether your furnace frequency is calibrated to measure or melt that kind of small size scrap. If that is both
Yes.
taken care, you can melt borings.
Yes. Secondly, there will be a lot of slags formed with iron oxide.
Yes.
That continuously you have to go on steaming it.
Yeah,
Okay.
that is rightly said, sir. When you have tried to remove all the coolant, you tried to have it dried, then you are getting it rusted. When it is rusted, slags are high. Either you remove the slag. If you don't, it can end up in your casting. That's the danger.
Correct. That is correct. You're perfectly right. Thank you very much.
Thank you, sir.
Okay, sir. Thank you, sir. Okay, thank you.
Yes, sir. I
Sir,
see a hand up.
Sir, I have one question, sir.
Yes, sir.
Sir, even trace elements individually controlled, but cumulative of trace elements will affect shape and size. Kindly clap, please.
Yes, sir. Definitely. It will synergize with other elements and cause a problem. So to keep a trace of how much it is being built up in your system, the first thing to do is to get the CRMs in your OES, which can measure them correctly. And the second thing, there is something called Tillman's factor, which actually summarizes all these trace elements, and then it has an equation. If it is less than 1, greater than 1, or more or equal to 1. So when you are having an Excel sheet which summarizes your daily chemistry, it's very easy to add that formula and then monitor. When you see a problem arising, you can go back and see this has caused a problem or not. So this is something that we can do with simple OES. An advanced version is that if you are having thermal analysis system, you can actually see the difference of these trace elements in your cooling curves, the impact of that. You would see an extremely low solidification temperature. Your metal will not solidify at 1100 degrees Celsius. It might come down much lower than 1100 degrees Celsius. You would see a very high G3, a very low G3 values, late stage graphitization will go down. So a thermal analysis system is a very good tool to actually see this impact, and also a tool to see how we can correct it. So typically, since most of the foundries operate at OES, I would suggest get the correct CRMs for the OES to measure these trace elements. Once that is done, then you actually include Tillman's factor into your trace elements and keep an eye out for it.
Okay, sir. How we control the even this is a rational number. How we control in charge material, sir?
Sir, in charge material, you see a trend of seeing that, okay, I am using 60% scrap, I am seeing using 30% returns and rest is my alloying. And then you are seeing slowly your titanium is building up. Then you find out whether the titanium is coming from scrap. Then your purchase says that you have to use this. Then you have to think about way of neutralizing it. That is where the preconditioning comes in.
One
So I
way
have to
neutralizing the metal part.
neutralizing Tamila sir நீங்க
இல்ல சார் அது வந்து இப்போ
ஆமாம் சார். இப்போ டைட்டானியம் நான் சொன்னேன்ல சார், அது தனியாக பிரிஞ்சு வந்தால் தான் எனக்கு மெட்டலில் பிரச்சனை பண்ணும்போது அந்த டைட்டானியம் நான் என்னோட ப்ரீ கண்டிஷனர் யூஸ் பண்ணி அது ஒரு காம்ப்ளெக்ஸ் ஆக்சைடாக கொண்டு போயிட்டேன்னா அது வந்து உங்களுக்கு பெனிஃபிட்டாக தான் இருக்கும். அது உங்களுக்கு பிரச்சனை பண்ணாது. அதுக்கு தான் கரெக்டான ப்ரீ கண்டிஷனர் ஆட் பண்ணோம்னா அந்த பிரச்சனையை சால்வ் பண்ணலாம். உங்களோட கேள்வி ரொம்ப வேலிட். ஏன்னா யூ வில் பி ஃபோர்ஸ் டு யூஸ் சர்டன் ரா மெட்டீரியல்ஸ் ஃபார் மார்க்கெட் கண்டிஷன்ஸ். ஐ யூஸ் தட், பட் ஐ நீட் டு ஹேவ் அதை நான் எப்படி அதை சரி பண்ணி யூஸ் பண்ணணுன்றதை நீங்கள் பார்க்கணும் சார்.
அதுதான் சார் கேட்குறேன், வேற ஒன்றும் இல்லை. நம்ம கண்ட்ரோல் பண்ண முடியாது, பட் நியூட்ரலைஸோ இல்லை அது வந்து எஃபெக்டை சிவியர் கம்மி பண்ணுறது.
ஃபர்ஸ்ட் திங் அதுக்கு நான் சொல்கிறேன் சார், மெஷர் பண்ணணும். கரெக்டாக இருக்கு அதுதான் பிரச்சனையான்னு தெரியறதுக்கு ஃபர்ஸ்ட் மெஷர் பண்ணுங்க. மெஷர் பண்ணி அதுதான் பிரச்சனைன்னு தெரிஞ்சதுக்கப்புறம் நியூட்ரலைஸ் பண்ணுறதுக்கு நம்ம ப்ரீ சீடோ இல்லை ப்ரீ கண்டிஷனர் கொடுத்து சரி பண்ணலாம். பட் நமக்கு அதுதான் பிரச்சனைன்னு தெரியறதுக்கு முன்னாடி ப்ரீ சீட் போடுறதுன்ற ஒரு அடிஷ்னல் காஸ்ட். அதனால தான் சொல்கிறேன், ஃபர்ஸ்ட் நம்ம கரெக்டாக மெஷர் பண்ணுவோம், அப்புறம் நியூட்ரலைஸ் பண்ணுவோம்.
ஸோ ஈவன் ட்ரேஸ் எலிமெண்ட்டாக இருந்தாலும் நம்ம வந்து மானிட்டர் பண்ணணும் ட்ரெண்டை.
ஆமாம் சார், அதுக்குன்னு உண்டான சிஆர்எம் வாங்கி நம்ம கரெக்டாக அதை மானிட்டர் பண்ணாதான் சார், மெஷர் பண்ணாதான் அதை நமக்கு நம்ம எடுக்கிற ஸ்டெப் அது கீழே எடுக்கிற ஆர்சிஎல் நம்ம போடுற ஆக்ஷன் கரெக்டாக இருக்கும். அது இல்லை அப்படின்ற போது நம்ம ஏன் தேவையில்லாமல் அதில் எஃபர்ட் போட்டு தேவையில்லாமல் காஸ்ட் இன்ட்ரடியூஸ் பண்ணணும் சார். அதுக்கு தான் சொல்கிறேன், ஃபர்ஸ்ட் மெஷர் பண்ணுவோம் சார் கரெக்டாக.
ஓகே சார். இப்போ வந்து நம்ம இனாக்குலேஷன் அது மீன்ஸில் நம்ம வந்து அதை இப்போ இது பண்ணலாமா சார், சொல்யூஷன் கண்டுபிடிக்கலாமா, சால்வ் பண்ணலாமா?
சொன்னேன் இல்லை சார், இப்போ டைட்டானியம் ஜாஸ்தி இருந்தால் அந்த ஷேப்பு சைஸ் எல்லாம் அஃபெக்ட் பண்ண போகுது, ஒரு நாடிலோட ரவுண்ட் ஷேப்பை கெடுக்க போகுது. அப்போ நான் நார்மலாக போடுற இனாக்குலண்ட்டோட வேறு ஏதாவது பெட்டர் இனாக்குலண்ட் போட்டால் என்னால் கண்ட்ரோல் பண்ண முடியுமானா கண்டிப்பாக பண்ண முடியும். அதுக்கு முதல்ல எவ்வளோ டைட்டானியம் போட்டு அங்கே அதுக்கு நான் இனாக்குலண்ட் போட்டு கரெக்ட் பண்ணுமா, ஃபர்ஸ்ட் திங் நான் என்ன பார்ப்பேன்னா சார், எவ்வளோ டைட்டானியம் இன்க்ரீஸ் ஆகிருக்குன்னு பார்ப்பேன். அதை எனக்கு ரெண்டு ஆப்ஷன் இருக்குது, பேஸ் மெட்டல்லே கரெக்ட் பண்ணலாம், இல்லை ட்ரீட்மெண்ட் பண்ணதுக்கப்புறம் கரெக்ட் பண்ணலாம். எது பண்ணால் எனக்கு பெட்டராக இருக்கும்னு கேட்டிங்கன்னா என்னை பொறுத்த வரைக்கும் பேஸ் மெட்டல்லே கரெக்ட் பண்ணால் பெட்டர்.
Can you answer in the English, please? There are
yes,
other
sir.
people
So,
who are listening.
I extremely apologize for that. What I was trying to say here is that when sir raised the question that I will speak in English.
Okay, because you are attending only one person, but listeners are so many people. That will also benefit to them.
Sure, sir. So his question was that how do can I correct the impact of titanium with inoculation? That was his question, sir. So yes, I told him that as the first thing I would do is to measure the titanium accurately. Once correct. I know that titanium is the problem, then I'm going to see how I can rectify it. There is two options for me to rectify. I can rectify it in the base metal itself or post treatment with inoculation. And with whatever interaction we had, limited data I have, I would suggest that I would go and try to correct it in the base metal.
Okay. Just to add to your subject, most of the people use steel as a come down of the carbon in the pig iron. The steel percentage may contain high titanium. Several steels are deoxidized with titanium oxide. The trace element of titanium goes in the steel, and if the same steel used as a scrap for melting of the pig iron to reduce the carbon, that titanium is automatically get accumulated in the cast iron, and that gives a side effect in the total in properties.
So correct, sir. So I would not then use pig iron, no, sir, to neutralize it. I would use something else.
Yes.
So we have worked on Elkem on multiple products. We are trying to have a new product also in to specifically target this problem. So pig iron is not, it was a solution, but now we have much better options than that because the titanium is going to increase high.
Yes.
Okay, sir. Mr. G. Kumar has raised his hand.
Yes, sir. I have one question.
Yes, sir.
Last some days one of the slag accumulation more. Any trace elements there in some reason,
Sir, you are having slag. One thing, trace elements is not going to cause you that much slag increase, because as the name says, the trace, they are very less. It cannot promote so much amount of slag. But if you are having high calcium, highly rusted scrap, or if your lining is not great, or if the ladle is kept idle for a longer time between tappings, then that can be a reason. If you're seeing it only in the last couple of months, I would go suspect the charge mix, the condition of the charge mixer.
Charge mixer has not followed the last 2 years one charge mixer. Because of last some days only now accumulated more of slag in furnace. That only I've laid any thermometer out. That only I.
What is the charge mix you use, sir?
Not only the charge, but if you raise the temperature on higher side more than required, or you superheat, much of the iron gets oxidized, converts into slag.
That's absolutely
yes, I know, but we are using 15 to 20% of HMS, 10 to 20% boring. But the temperature tapping is 1520 and 1530. But slag accumulating more of last. Well, we are using borings only.
Sir, where are you from, sir? Where is your foundry, sir?
TVS SFL Foundry.
Where, sir?
SFL, Sundaram First Limited, TVS Auto.
SFL, no, sir.
SFL
I'll talk to you, sir.
Okay.
I'll talk to you, sir. Kumar, sir.
Okay, sir. No issue.
The slag formation is in 3 grades. One, higher oxidation. Secondly, excess of silicon. All slags are made up of silicon only. These are called as the silicides. So excess of silicon, excess of the carbon, excess of the oxidation of FeO because of high temperature. People are tapping with 1480 or 1590. Why you are going to 1520, 30? I don't know. So you reduce the temperature in the furnace, you may get down the slag formation. Secondly, slag holding compounds are available. So that will collect all the slag and you can remove it. It is hardly 1 or 2%. Slag formation is not a problem in the present context.
Yes, sir.
Thank you, sir.
Thank you.
Kumar, sir, I'll make a visit. I'll help you to solve this issue. Don't worry.
Okay. Thank you very much, sir.
Hello.
Hello, sir. Tell me, sir. Hello.
Any other questions?
Sir, if there's no more questions, we can close this thing. So hope actually there's no more questions. Okay, sir. As we conclude this highly informative webinar on effect of trace elements in cast iron, Boon or Bane, it's my privilege actually to propose the vote of thanks on behalf of Indian Institute of Foundrymen Chennai chapter. First and foremost, I extend my deepest gratitude to our esteemed guest speaker, Mr. Balaguru Sendil, Deputy Manager, R&D TCS, Foundry Elkem Innovation, for his brilliant and thought-provoking presentation. Your expertise and the depth of knowledge you shared actually with us today have provided valuable insights that will undoubtedly benefit all of us in our respective fields. To all the participants, thank you for your enthusiasm, engagement, thought-provoking questions, and active participation, which made this session truly enriching and interactive. Thank you once again for your presence and contributions. We look forward to welcoming you for future events. Have a great day ahead. Thank you.
Thank you, sir.
Thank you.
Thank you very much, sir.
Thank you, Mr. Balaguru. Thanks to all the participants. It was a wonderful presentation. Thanks so much.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir. Thank you.
Thank you so much, sir. Thank you, sir. Thank you.
Thank you, sir.